Okay, in this video, I'd like to show you how to arrive at this expression here, this equation that relates or shows the difference between the heat capacity at constant pressure, molar heat capacity at constant pressure, and the corresponding molar heat capacity at constant volume. So as you can see here, is equal to temperature, the molar volume, the expansion coefficient squared over the compressibility coefficient. So let's see how we get here from the fundamental first law of thermodynamics. Okay, so starting with this statement of the first law of thermodynamics, delta U equal Q plus W, we attempt to get here. Okay, so let's start. Okay, so we can rearrange this expression to show that Q is equal to delta U minus W, which is equal to, if we express this in terms of D differentials, dq equal Cp, Cv dt plus du dv constant T dv minus work. Recall, work is defined as minus P external dV. So then this term with the minus and the minus becomes a plus. It's going to be plus P external dV, right? Okay. No need to panic. Delta U, which is related to du, right, is equal to Cv dt plus dependence of U with respect to volume times dV. So this is something we did in class already. So we're using previous knowledge. Okay. So now we are going to add a constraint to this equation. Let's say that we're going to consider the process to be at constant pressure. That is, that P external equal P, constant. We will indicate that dependence on the heat, right, that the heat is being occurring at constant pressure, so we put the label or the subscript P equal Cv dt plus du dV dV. Well, if you think about it, there is a dV here and there is a dV here. So that's like a common factor of this term plus P, that being a constant factor, common factor for dV. Okay? So P external is just P. We have dV and dV a common factor, so nothing weird going on here, just applying basic algebra here. Okay, dqp. We learned in class that this can be calculated as Cp dt. Right? So again, we're using previous knowledge. dqp equals Cp dt. So this is going to be equal to Cv dt plus this term here, du dV. We learned in class as well that this term is equal to T dP dt constant V minus P. This whole thing is this du dV. But we still have this plus P to take care of. Right? dV. Okay. Good. So what can we do now? Well, we see that this P goes or cancel with this P. So the expression now becomes Cp dt equal Cv dt plus T dP dt constant V and then this dV. What can we do next? Well, we can divide the whole expression by dt. So if we do that, then you have Cp equal to Cv plus T factor of dp dt constant V, then this dV dt, the next one, dV dt. Don't forget that this whole thing is at constant pressure, so I put a P here. Okay, so this is how much we have advanced. You can see now that it starts making sense in terms of the connection with the goal that we have. Cp, Cv, Cp, Cv. They are now here. We'll take care of the molar component later, but let's see what emerges. 1. This equation here allows me to calculate Cp minus Cv if I know, for any function of which I know the pressure and volume expressions as they depend on temperature and as they depend on temperature, right? So if I have an ideal gas, or if I have a real gas being a van der Waals gas, or any other kind of approximations to real gases, and I know the functional dependence of P and T, then I can get this term. And if I know the functional dependence of V and T, then I can get this term. So I can find Cp minus Cv for any kind of gases, right? But in particular, we are interested in getting there for now. So I can see here that, well, let me actually erase so that it doesn't get too crowded on the bottom. So I will go back to this part. Okay, here we are. I can say Cp equal Cv plus T dP dt constant V, and then this dV dt. Recall, beta was defined in class as 1 over V dV dt, constant pressure. Do you guys know what the name of this is? Well, this is the isobaric, constant pressure, isobaric volumetric expansion coefficient. So we had dV dt, constant pressure, equal V beta. So if I go back to this original equation here, then I can say that this is equal to Cv plus, oh, I was missing here, dV dt constant pressure. I was missing that. Okay, so I have Cv plus T dP dt constant volume, and then dV dt is going to be V beta or beta V, whichever, any way you want to put it. So we had the beta V, so somehow we need to get another beta and a K or a kappa in the denominator. So that must come from dP dt constant volume. That must come from there. So we'll do that right now. Okay, so take a look at this. Let's do it. Let's use the red one now. So the deal here is the cyclic rule. The use of the cyclic rule, you guys remember, dP dt constant volume times dt dV constant pressure times dV dP constant temperature is equal to what? Think about it. Where I erase this. Well, it's equal to minus 1. I'm interested in dP dt. dP dt. So I solve for it. dP dt, some volume is going to be minus, so move these two terms to the other side. It's going to be equal to dV dt, constant pressure, let's go to the other side, and then dP dV, constant temperature. Okay? So take a look at this final expression here, or the one that we have arrived at this point. So dV dP, that again is beta times volume. So what we have here then is that this is equal to negative beta volume, that's this term here, the negative remains, and then dP dV. Well, recall another definition, kappa. Kappa was defined in class as minus 1 over V dV dP and temperature, right? So this term here, dP dV, is nothing more than minus 1 over kappa V, right? Look, if I move this to the other side, then you will have dP dV, constant temperature, equal minus 1 over kappa V. So instead of having this dP dV, I can just go ahead and multiply this by minus 1 over kappa V. So the minus with the minus will cancel. Volume with volume will cancel. So what we have then is dP dt, constant volume, being equal to beta over kappa, right? Okay, so in the next minute or two, we're going to be able to finish or accomplish our goal. What do I need to do? Move or replace this expression, dP dt, here with beta over kappa. So that's what we're going to do next. Okay. So then this is equal to Cv plus Cp is equal to Cv plus dP dt, which is nothing more than beta over kappa. Remember we had the T already there, kappa here, and then beta B, which is equal to then Cv plus T V beta squared over kappa. Okay, so how do I get the M? Well, what you need to do is divide by n the number of moles. If you divide by n this quantity, then we end up with our desired final result. Okay, so that's the next 30 seconds. We're going to do that. Okay, so then, so far we have Cp equal Cv plus Tv beta squared over kappa divided by n, every quantity, then we will have Cpm equals Cvm plus Tvm beta squared over kappa. And then moving Cv to the other side, we have what we wanted. Okay. So here is our final result. And a comment before we go is that this difference will always be a positive quantity. Look, T, absolute temperature, always positive. Volume is always positive. Kappa and beta, these coefficients we learned in class, are defined to be always positive quantities. So this difference is going to be always more than 0. So Cp is therefore larger than Cvm. Cpm is larger than Cvm, regardless of the system. Great, thank you very much. Have fun.